Right, we're just going to take you through the first part of Chapter 10, which is the standing waves this morning. What we're going to do is look at the ideas briefly, but although most of it is in the PowerPoints that I've put onto Moodle and onto Teams. But if you have a look at these, what we'll do is we'll talk you through some of the ideas as we're going along. So, the basis for the whole chapter is on this idea of superposition, and that is literally down to the height of a wave, its displacement from the zero line at any point in time through the wave. If we've got two waves and they're travelling in opposite directions, then in my diagram here I've got my red wave travelling to the leftwards, okay, blue wave travelling rightwards, and at different points they reach different points in their cycle. So in the first instance, the red wave is 0 at this end position, but the blue wave is at a maximum. If we add those together, well, the maximum plus 0 gives you the maximum. Here, for example, I've got that height, that displacement downwards twice, so actually its peak there is twice as high as the peak of each of those, or the point of each of those at the moment, and so on. And there are some bits, for example, like here, where these two are actually the same displacement, but one's positive, one's negative. So if you add them up, they add up to 0. If they are completely out of phase or anti-phase, so one's going up as the other one's going down, then every single part of it will cancel out. If they are both in phase at that point, then you're going to end up with a wave, a resultant wave that's twice the amplitude, twice the displacement at every single point in the cycle, but the peaks are at twice the amplitude. Now, we can get this in lots of situations. We can actually have one wave reflecting off, and therefore it's producing a copy of itself, and the copy meets and superposes, adds onto the original wave. Now, a classic example of that is strings. Guitar strings work as you pluck them, you're sending a ripple one way along the string and the other way. What they'll do is they'll reach the ends where they can't vibrate, and so they reflect off those points and they'll come back in, and wherever they're crossing over you end up with these positive and negative waves building up. If the wavelength just happens to fit in nicely with the distance between the two ends of the string, then you start to see what we call standing waves. They stand up higher in some points. There are some bits where they don't seem to vibrate at all. The waves are still going left and still going right, but what you find is that, like in these diagrams, there's certain points where actually they always happen to add up to 0. Yeah, so we've got 0 there, 0 there, 0 there, and those points will always be 0 as the red and blue waves cross over. Those points where they add up to 0 is what we call a node. That's where you've got no vibration at all, there's no energy, and quite easy, very clear points to see, so it's very easy to measure those points or those positions. And then in between, the waves just get higher and higher, reaching a maximum point called the antinode. Now, the antinodes and the nodes have to fit in that section. If they don't fit in that length, if the frequency being created, for example, in this case with a vibration generator, if it happens to be wrong, then what you'll find is that these peaks will just move up and down. They won't be standing still. They won't be stationary. Okay, so you actually need the right frequency to produce the right wavelength of wavelength of the wave. So that it just happens to fit in, and as long as there's a node at each end, then it will keep reflecting back and forth and you'll get a nice steady wave. Okay, so that limits how many peaks we can fit in a section of wave. So, although they're actually made from waves that are moving, it appears as though they're standing still, but there is a big difference between them. So the progressive wave, as they travel back and forth, as they wash up and down, at some point every single particle in that wave will reach that maximum amplitude. In a standing wave though, what we find is that the amplitude of every particle has its own different amplitude. So every particle has a different single amplitude. Positive and negative, but at each point on that wave it's either going to be vibrating up and down a lot or vibrating up and down a little bit. If I just give you a little sketch here, and we're just going to draw a wave clamped at the two ends, so I have my two nodes, okay, node and node. Well, at a moment in time, that string, for example, has reached all the way to the top. A bit later, it's going to go lower, then lower, and keep going lower until it actually gets to its maximum downwards position, and then it will go back up again progressively. So all of those are moving together. It's just that the peaks in the middle, well, they're going to move obviously all the way from this point up here down to here. So its amplitude from that middle position is that high. But the peaks over here, they're not going to vibrate as high, and they never will do. Not as much as they will in the middle. So every single point along this wave has a different amplitude. And that's obviously very different from a travelling wave, from a progressive wave. Now, the frequency is the same. Okay, so all of the waves have the same frequency, and that will be the same here. So again, all points have the same frequency. But where that frequency fits or not is what produces the actual wavelength itself. Now we can't see it, as I say, if it's moving along, but if it's standing, then what we'll find is the wavelength is actually fitting into those fit lengths. So the distance between nodes is always going to be the same amount of a wave. It's always going to be is half of wavelength. Okay, so it's half of lambda. So it doesn't matter where you do them. If you want to go from the antinode to the antinode, that is also going to be half a wavelength, but it's much easier to measure from the nodes. Now the phase, very different. Again, as I've just kind of shown you with that, with my diagram, my quick explanation there, that's very different. With the progressive wave, effectively it's that idea of that curling through space. So it's some points are higher, some parts are lower, some points are at different points in the cycle that are very high, and some are at zero. But if you're in phase, if we're talking about phase in a standing wave, what you'll find is that each half wavelength, so each distance between every node, all of the points in that section are moving in phase. So all of that section that we just sketched, they're all moving up at the same point, they're all moving down at the same point, so at the same time, so they're in phase. The next section, beyond the node, is actually out of phase, it's anti-phase. It's going down when the first half is going up. So effectively you've only got two phases in a standing wave. It's either on its way upwards or it's on its way downwards, and there's no part of the way upwards, it's all moving together. And what that means is that the energy, instead of being washed along with this phase change, what you're actually finding is that the energy is trapped. So it's a useful idea where you've got the maximum at the maximum amplitude, with the maximum at the antinode, or antinodes, shall we say, okay. And no energy at all at the nodes. However, you are getting, as I say, that kind of idea where you have this probability of energy being being stored at different places in a cycle. And we can model that, and we can use that explanation to explain why we are more likely to find electrons in a certain point in an orbit, or how many electrons we're finding in an orbit. So we can do that. The guitar string, the sound doesn't wash away, it still just sits there vibrating, and you can hear that vibration as the note rolls on. And it does with anything that's moving in this particular way, which is generally what we call simple harmonic motion. It just keeps rattling away. Now, using those two ideas and this idea of half wavelength, we can start looking at things with a bit more interest and examination. If, for example, we're looking at some sort of closed-ended pipe, this could be you blowing across the top of a milk bottle or a beer bottle, what you'll find is, of course, it's really nice and loud, and that's because the wave that you're creating, the vibration that you're creating here, has a lot of energy at the opening. But what the wave is doing is it's heading outwards and dispersing outwards into the air, but it's also trapped within the bottle. So what you'll find is it will reflect off the bottom, and because it's reflecting, you've got a node at that point, and it will reflect out to reinforce the sound. So you blowing isn't very loud, but you blowing across the top of the bottle's air is actually increasing the vibration, it's increasing the energy at this point. So this is going to be nice and loud if it's a sound wave. We can do the same thing with light. It's obviously a bit harder, but we can do the same thing. Now, in the video, you've got a short clip of my son playing his tune. On his cornet, he has to go through and practice doing different modes. So he blows harder, and if you do the same with a bottle, you can get a higher note out of it, and you blow harder again, you can get a higher note out of it, so the wavelength is trapping. We still have the points which we have the node, where you got a reflection, and a loud bit, which is the antinode, but you're actually managing to creep in an extra half wavelength. So here we've gone from a maximum point down to a minimum. This is actually a quarter of a wavelength. Bit hard to see, but if we add half a wavelength, you can see it's a bit more like most of a wave now. It's about 3/4 of a wavelength. And if we go to the next one, then the same idea again. You blow harder again, you get that next highest note up, the next harmonic as it's known. And that idea is that, again, we fitted in another half wavelength. So we've now got 2 half wavelengths plus that original section. So we've actually got 1 1/4 wavelengths trapped in there. And every single time we go up a mode, every time we go up to the next harmonic, the next harmony, to make it sound in phase, it sounds natural, we're adding on half a wavelength. So from that we can do the maths, and it's nice and straightforward. We tend to use this symbol as the fundamental frequency in any system, where this would be a little bit higher. And if you do the maths, well, I've now got 3/4 compared to 1/4, so it's 3 times shorter wave, so it must be 3 times the frequency. And if we go up there, we've got 5 times the length of wave in that same space, so it must be 5 times higher the frequency because the wavelength is 5 times shorter. So, yeah, 5 times, if not. And we can go through that, and we can go up in different modes. But it's all about that visualization of trying to figure out how much of a wave you've got. Really hard to do, but quite straightforward, very easy to go up to the next note, and you know that you've just increased it by half a wavelength. Now, those are what we know for closed pipes. That means they're closed at one end. Quite often, for example, in a microwave oven, that's tends to be how we kind of amplify the microwaves in there. So you do get some dead spots with no energy, and that's why your plate rotates in the bottom, so that that bit of food doesn't stay in the bit where there's no energy. It rotates into one of these bits, and so everything cooks through. What that's representing, of course, in this diagram is a sound wave, and it's actually about the movement of the air. It's not a transverse wave, it's a longitudinal wave. But if we think about what it's representing, well, the air's moving fastest, it's moving more, so therefore it's got more energy at the entrance, whereas down at the bottom you're getting very little movement at all. And it doesn't matter whether you've got the wave going in or the reflected wave coming out, you've got the same symmetry. So what this shows is actually a graph of the amplitude, the movement, the rate of movement of the actual the air particles. Okay, more obvious are strings. They're a bit more kind of usual because a lot of things tend to appear like this. Although to be fair, you could model this as the vibration of, for example, a ruler on the table. The bit that's leaning on the table doesn't move, so that's your node, and then the loud bit with the large vibration, that's your antinode. If you put it on its end, that could be a building clamped on the ground, and the top vibrates if, for example, you've got an earthquake wave making this vibrate. So we can use this explanation for lots and lots of different places. The most common that we tend to see is with basically guitar strings. So what we've got down here is what you would normally see if you were to pluck a guitar string. That's a node at each end. That's your reflecting surfaces. So we must have an antinode in the middle, and if we use the idea of that, well, hopefully you can see that that's going up. The next bit, if it's going down because it's out of phase, that will give you a full wavelength. So that is half a wavelength. So the wavelength of this wave would need twice the length of string. Now if we go to the next one, again go up a frequency, so you go to the first harmonic, well, we need to, just like above, squeeze in an extra half wavelength. So we've got that, so that looks more like a full wave, and then half a time period later it's swapped over, then it's going to swap back again. Okay, so the two halves are vibrating in opposite directions, but that, I think, is fairly obviously the wavelength is going to equal the distance between those. And what you've got is that must be half the length, because you've now got two of them in the same space, so it must be twice the frequency, 2f0. If we go up to the third harmonic, well, I need an extra half wavelength, so I'm going to go up, down, and up again. Bit short that last one, never mind. So effectively, yeah, I've now squeezed in that extra half wavelength, and just like all of these systems, it's always adding that extra half wavelength. So our wavelength is 2/3 of L. Okay, so it's getting shorter and shorter and shorter, the wavelength, because it's going up and up in frequency. And if you want to think about that and work it through, it's third of that wavelength there. Okay, the full wavelength was there, but that's now been shortened to a third of it, so that must mean it's 3 times the frequency. All, of course, assuming that it's travelling at the same speed through the string. So as long as you haven't played the string differently, you can still get that to work. The speed of the wave as it travels back and forth will still be the same speed. So therefore, yeah, if you're shortening the wavelength by a factor of 3, you must be increasing the frequency by a factor of 3. If we go up again, next harmonic, well, effectively we're getting 2 lots of waves. Yeah, because I've just added another half wavelength. So now the wavelength is half of L. Yeah, and so that must be 4 times the frequency. And with this string system, it's much easier to think about the harmonics. These ones behave in a certain way. If I open the pipes, they go up in certain ratios. But if you're going with the strings, the harmonics are simply 2 times the frequency, 3 times the frequency, 4 times the frequency, 5, 6, 7, 8, 9 times the frequency, as you fit in that extra half wavelength every single time. In terms of wavelength, there's a bit of a pattern as well, in that actually you can start thinking about the different bits. So that's 2 over 2. You can make that 2 over 1 if you prefer. 2 over 3, 2 over 4, 2 over 5, 2 over 6, 2 over 7. So you can relate it through, and there is symmetry in all of this, because if you think about it, it must be symmetrical about how it goes. So what can we do? Well, we can change the notes, we can change the systems, and that first page has a classic experiment that's it's not one of our controlled assessments. It is for the AQA, but for OCR we do a different one, which is using the pipes, because I think it's much more clever and useful to know. But what you can do is change the guitar string, because that's effectively what this is. And what can you do to a guitar? You can tune it by tensioning the string. Yeah. So again, on the PowerPoint, it's got a close-up of the strings. You could have a tighter string. You could have a thicker string, so bass guitars with the lower notes, the strings are much thicker. But again, if you look at the guitars, a standard electric guitar, the actual thickness of the wires changes anyway. And that changes how quickly the speed is going through the wire itself. So we can break it down because it's nice and straightforward, and we get something called the Mersenn's law equation. Okay, which looks kind of complicated. You don't need it for your data sheet, but I want to show you how this works, because these are actually just the wave equation. So if we take velocity of a wave, we know its frequency times by the wavelength. And if we say the fundamental frequency, then that will make it a little bit easier to do. What we can tell from the guitar string just over the diagram that we've just looked at, we know that the wavelength is 2 lots of L. So what we can say is wavelength equals 2L. Okay. Well, if I take those two facts there and look at this underneath, what effectively I've got, if you cross multiply this, is if we take our 2L up there, we've got 2L F naught equals root T over mu. That's our wavelength, that's our frequency, so this must give us our velocity. Okay, so what we're saying with this, and again, if you happen to have a guitar or want to look online and have a closer look, if you change the tension in the string, then the velocity gets higher, and because of that tension getting higher, our frequency goes up, our note goes up. Yeah, so a tighter string has a higher note. A tighter vibrating ruler, a stiffer ruler, has a higher note. So it kind of runs through everything. And this here is the mass per meter of the material that's actually vibrating. So it's basically the number of kilograms per meter of the string. So the thicker the string, what you'll find is the bigger that number is, the smaller that number, the lower the note. Yeah, and we can check it all through because we can work out the units for it. So frequency is, just put the links on here. Frequency is hertz, which is seconds to the -1. Okay, length is in meters, obviously. And tension, well, it's a force, so that's newtons, but a newton is mass times acceleration. In kilograms, mass times acceleration, and seconds to the -2. So if we put all those together, what we can do is, if I'll rearrange this, so I'm going to go for F naught squared, okay, times by, I'm going to take these up here, so 4L squared, okay, that's going to equal T over mu. So I'm going to swap those around. Mu equals T over 4L squared F naught squared. T is going to be its equivalent in units is kilograms, meters, and I'm going to put seconds down here, squared, because the minus just means it's per. I've got my length in meters, so that's going to be meters squared, and we have our frequency in seconds, but it's squared, so that's squared, so it's going to be seconds minus 2, but I'm going to swap that up to the top because that makes it seconds squared rather than those. And I've got that and that. One of my masses crosses out with that, and so I end up with kilograms per meter. So yeah, mu, the unit of it is kilograms per meter, so therefore it must be mass per unit length. Okay.